Okay, continue on with question number 5 from exercise 1D, proof by deduction, the intermediate questions. Let's go. So prove that the height h in the diagram is given by this, h being equal to ab over the root of a squared plus b squared. Now with this, it's often quite tricky to know where to begin, but you've got to look for clues in the question. So I can see I've got an a times a b, okay, and how can I get that from this triangle over here? Well, a times by b, I'm thinking area of a triangle at some stage along here, okay? And then this bit, the root of a squared plus b squared, this is actually using Pythagoras to find the longest side in a triangle. Okay, this is how you would write it. Okay, so I'm thinking area of a triangle. Let's begin with that. So let's consider this triangle here. Okay, and go from there. So let's consider this triangle, bam, up here and then down through here. So that's really messy and I don't like that. Let's go from here up to here and then down to here. And let's draw that over here. So I've got this triangle up here and then down by here. And I've got this right angle, which is going to be really useful. And I know that this side here is going to be called side A, and it's going to be called side B. Sorry, it's getting really messy, side A and side B. And this is good because I know that the area of a right angle triangle, A, is equal to half times the base times by the height. So that's going to be a formula that I'm using in this. That's the area of a triangle formula. So going back to this triangle here, I can define this area to be, well, the area is equal to a half times the base, which is A in this case, times by the height, which is B. So this is like kind of one formula, okay, that I've just derived. And it's useful because I can see I've got this AB, which is the AB up here. I've got a half here, which isn't particularly useful. What I'm thinking is if I can define the same green triangle and get the area of it, but using different lengths, so this length down here, okay, and then the height, because I also need the letter h in my equation, then I'm going to be good to go. So this is good, looking good so far. Right, this here you need to recognize comes from Pythagoras, and I'll go through it very, very quickly now. Okay, so if we have a right triangle, so like this, and like this, okay, we know from Pythagoras that these two sides here, A and B, are your short sides, that's your longest side, that's your right angle there, okay? And then we know that Pythagoras is a squared plus b squared is equal to c squared. Now if I wanted to go and write the longest side, c, on its own, so to find the longest side, I would square root both sides and say that c is equal to the square root of a squared plus b squared. So this here, so this c is the longest side in your right angle triangle, and you can define it to be the root of the two shorter sides squared, added together. So this, okay, is the same thing as this, which is good, which is going to be the longest side, so this one, okay, in my right angle triangle. So I can go and say, okay, that this root a squared plus b squared is this side here. So this is the root of a squared plus b squared, this side down here. Okay, so I can now go and get the area of this green triangle again, but this time using the base to be root a squared plus b squared, and then the vertical height to be h. So using the same triangle, okay, I can go and say that the area is defined to be, okay, half times the base. This time the base is that root a squared plus b squared. So let's go and write it. So root a squared plus b squared over here. And then we're timesing it by the vertical height, and it's got to be the vertical height, so h, which is over here. So half base times height, so half times by h times by this. I've just written it in this order because it looks a little bit nicer. Okay, so now I've got two different definitions for the same area of the triangle. I can put a and a equal to each other. So this is equation 1, and this is equation 2 over here. Let's go and put them equal to each other, and let's go and do it down here. So I can now go and say that half AB is equal to, because these are the same, they're defining the same area, but just in different ways. Okay, so half AB is equal to half times by h times by the root of a squared plus b squared. And this is really good because I can see in this I've got AB, which is looking pretty good to what I've got up here. I've got this root a squared plus b squared, which is also here. And I've got the letter h, which is good. What I notice here is that I can go and cancel the halves from both sides because they're on both sides, which is good. And I can go and divide the equation here because that's h times by everything here. I can divide through by the root of a squared plus b squared and say, okay, that h is equal to ab. I'm dividing through by the root of a squared plus b squared. And you can see, okay, this thing here is exactly what I wanted from the question. So I think a little bit tricky because you've got to kind of work out what to do in the question, but you've got to use the clues they give you. So AB, timesing the sides, area of a triangle, and then just defining it in two different ways. So this is one way of defining the area of the triangle. This is another way of defining the area of the triangle. Okay, so there we go. Question number 6 says, prove that the sum of the interior angles of a hexagon is 720. So this is saying that if you add together the inside angles of a hexagon, a 6-sided shape, you get 720. We've got to prove it. And actually this question is relatively easy. So a hexagon has got 6 sides. So 1, 2, 3, 4, 5, and then 6. Okay. And yeah, that's proof that the sum of the angles equals 720. So what I'm going to go and do here is I'm going to go and take a vertice and join up to the other vertices of the hexagon. And there we go. And with proof by deduction, you've got to really write out your argument in logical steps, okay? Logical reasoning. So we know, okay, that the sum of the interior, so the inside angles, sum of the interior angles in one triangle is equal to 180. So in one triangle, if I add together this inside angle, at this angle, at this angle, it is going to make a total of 180 degrees. Well, how many triangles have I got? I've got 1, 2, 3, 4, which must means I've got 4 lots of 180, which is equal to 720. So I can go and do, well, 4 triangles, which is what I've got, is going to be equal to 4 lots of that 180, which is equal to 720, okay, degrees, which is exactly what they said in the question. That is it for question 6. Okay, quite nice and straightforward, that one. Question number 7 is saying that prove if a number leaves a remainder of 2 when it is divided by 3, then its square leaves a remainder of 1 when divided by 3. A lot going on there. Let's just consider this top line to begin with. So prove that we have a number that leaves a remainder. So we have a number, okay, that leaves a remainder of 2 when it is divided by 3. I've got to try and write this algebraically because with proof by deduction, you've got to prove it for all cases. But just to think about what this really means, it is saying, if I took something like, I don't know, the number, if I took my number to be 17 and I divided it by 3, okay, we know, well, 17 divided by 3, kind of using like primary school terms really, is going to be equal to 5, remainder 2, which is good because the question is saying you want to get some number, I've chosen to be 17 here, we're going to write it algebraically later. I divide it by 3, which is what I want up here. I get some number, which is equal to 5, and I get a remainder of 2. Okay, but how can I write this a little bit more formally? Because this isn't particularly good at this stage of where we're at. So how can I write this remainder 2 a little bit nicer? I can write this to be the same thing as 17 over 3 being equal to, I've still got that 5. When you've got a remainder of 2 and you're dividing through by 3, we write this as plus 2 over 3. This is exactly the same thing as this. So the right hand side and this mean the same thing. Type it into your calculator, you will see if you do 17 over 3, take away 5 plus 2/3 is equal to 0. So 5 remainder 2 you can write as 5 plus 2/3. So now if I go and write this, now using that knowledge, okay, I can write this first statement using some algebra. So I'm saying that I take a number, so I take a number, n, I've called it n, so my number is n. I divide it by 3, okay. Well, if I do that, I must get some number, okay, in my case here, right, that n was equal to 17, but I'm now defining it to be n, because it could be any number. I divide it by 3, I get it equal to, I get some number, so some different number, which let's go and call it q, because why not really? And then remainder 2, we said you could write okay, remainder 2 as 2 over what you're dividing by. So q plus 2 over 3. But I want to write my algebraic equation here in terms of the number because that's what I'm looking at here. So let's go and times through everything by 3. Because if I do that, then the 3's are going to cancel and we'll get n to be equal to 3q plus 2, because this 3 are going to cancel, the q gets times by 3. And this is now good, because I've now defined that first line in terms of some algebra, which is really useful. The second line is saying then we take the square of this number, okay, and we're saying it leaves a remainder of 1 when divided by 3. So that's what we're really proving. We're proving that if we take this number and we square it, we get a remainder of 1 when divided by 3. Okay, so let's take this number here and let's go and square it. So we're going to go and take n, I'm going to square it. So we're going to get 3q plus 2, and we are squaring it. Okay, so now that's going to be equal to, well, if we go and expand this bracket, hopefully this bit is okay. I'm not going to go through the expansion, but that will give you 9q squared plus 12q plus 4. Okay, if that's confused you, expand 3q plus 2, bracket 3q plus 2, and hopefully you get to this. Now, the question is saying that we get a remainder of 1 when divided, okay, oh, sorry, what's happened there? We get a remainder of 1 when divided by 3. So if I can sort of factorize out a 3 here and get a 1 on its own, that's going to be a good thing, because what it's saying here is, like, for example, if I had a number like number 13, okay, if I wrote 13, because 13 isn't divisible by 3, but there is a remainder of 1 if I divide by 3, because we get 3, 6, 9, 12 plus a remainder of 1. But 13 you can go and write as 12 plus 1, which is useful because then you can go and factorize out a 3 from that 12 and get 3 bracket 4, okay, and you've got that plus 1 on the end. So it's really saying, right, if you were to take this and divide it by 3, okay, you should be able to factorize out a 3 from part of that number and have a plus 1 on the end, that remainder of 1. I want to do exactly the same thing with this down here. So let's go and do that. So I'm going to write this, being a little bit crafty, I'm going to write this plus 4, okay, as a 3 plus a 1, because then with the 9q squared plus 12q, okay, written really messily, hopefully you can read that, okay. I'm going to go now and factorize out a 3, so take out a 3, so we get 3q squared plus 4q plus 1. So what I've done there is I factorized this bit, I factorized out the 3, okay, but I've also got that plus 1 still on the end. And that's my answer, okay, so I've taken the square of my number, okay, I have a remainder of 1 when divided by 3. So if I can factorize out a 3 from part of it and then get a plus 1 on the end, it means that this part here is divisible by 3, okay, and I have that remainder of 1 at the end. And if I wanted to, okay, I could, like we did in the previous video, I could define this as something a little bit nicer, like I could go and call this x. Let's go and do that. So let's go and say that x is equal to 3q squared plus 4q plus 1, which then means, okay, that, so we've got this over here just to make things a little bit tidier. So this here is just some integer, it's just some number, so I should really go and write that down here. This x value is just some integer, okay, so I'm going to be getting 3 times by x plus 1. Okay, so this is answering my question, because I have a remainder of 1, okay, and this must have been divisible by 3. So there we go, okay. That is my proof by deduction. Okay, question number 8. So 2 parts to it. Part A is very straightforward, but then part B is saying prove that y is equal to x squared plus 4x plus 10 implies that y is bigger than 0. Well, let's just begin by looking at part A to get the ball rolling. So part A is saying, well, let's go and expand the first part, so x plus 2 timesing by itself, so x plus 2. Okay, because this one part of the question is saying expand it, really we should show our working, so let's go and do that. So x and this 2, there we go. And then we're going to get x by x is x squared plus 2x by 2x, so plus 4x, and then plus 4. There we go. Part A is done, which is nice. Part B is saying that proves that if we've got y equals x squared plus 4x plus 10, which is different to this, but kind of similar, okay, that implies that y is bigger than 0. Right. What I recommend you do here is, it's kind of, right, it's wanting you to use completed square form, because this here is actually in completed square form, and that's the hint to use to put this bit in here into completed square form. and you'll see why that's useful now. So if I take this here and write it in completed square form, we're going to get y is equal to, you get your bracket, square it, you take your x term, you half the 4x part 2, you square that 2 to get negative, to get a 4, but you always make it negative, okay? And then we have that plus 10 on the end. So this is, if you can't remember how to write things in completed square form, I have a video on that. So I've just written this here in completed square form. So then that's going to be y is equal to x plus 2 squared minus 4 plus 10 is equal to plus 6. Okay. Now, it's saying that if y is equal to this, I've just written it in a different form. So this thing here and this mean exactly the same thing. Okay, it is saying that implies, so if this is true, that must mean that y is bigger than 0. And what you need to spot here is, well, this bit here, okay, the smallest value that this part here, x plus 2 squared, can ever be is 0. Okay, because if we had the value of x, so if x was equal to minus 2, that's the smallest you can ever make this bracket, because we would get negative 2 plus 2 squared, which is equal to 0 squared, which is 0. Of course, if you made something like, I don't know, x to be minus 6, well, minus 6 plus 2 is minus 4. If you square it, you get a positive number. So the smallest that this can ever be is 0. Okay? So we can go and say, well, that what y, oh, let's do it in red, sorry. So y would be equal to 0 plus 6. Okay, so y must be at least greater than or equal to 2, 6, okay? Because if the smallest this could ever be is 0, which must mean that, well, if we had 0 plus 6, y must be at least bigger than or equal to the number 6, which indeed is bigger than 0. So if y is bigger than or equal to 6, that must mean that y is equal to 0. And that is our proof by deduction for question number 8. Okay. Question number 9 is this. Prove that the exterior angle in a triangle is the sum of the two opposite angles. Now, opposite angles in a triangle, it means the base angles in a triangle. So sorry, prove that the exterior angle in a triangle is the sum of the two opposite angles. So this one here, okay, if I go and draw a triangle just to kind of visualize what is going on here. Okay, there we go. Let's do it a bit bigger so you can see it clearly. So we've got this, and we've got this. Okay, so the exterior angle in a triangle, let's just go and choose an exterior angle over here. Okay, so the exterior angle I'm going to go and define to be x. So this angle here, I'm going to go and write as x. Okay, in a triangle is the sum of the two opposite angles. Well, opposite angles in a triangle are the two base angles, so that this one and this one over here. Okay, so I want to prove that this is the same thing as this and this. What I'm going to go and do here is I'm going to go and write this angle in terms of x. That could be a good thing to do. So let's go and write this interior angle in terms of x. That's going to be equal to, this angle is going to be 180, take away x. Okay, and then I know, let's write this out, I know that these angles here, so the opposite angles, so this angle and this angle, okay, add this angle must sum to make 180. So let's write it. So the opposite angles, okay, which are these two here, okay, plus this one, so plus 180 minus x, they must equal to 180. So in other words, to get the sum of my two opposite angles, okay, let's write it out. That's right, that these angles here, so this and this, right, these are my opposite angles. Okay, so to get those, I can go and do, well, in total, we've got 180 degrees in a triangle. If I take away this angle, that's going to give me what these two angles are equal to. So 180 take away 180, take away x, okay, and what's that going to give me? Well, these 180s are going to cancel, and then that negative is going to make the negative x positive x, so equal to 2x. So there we go. we've done it. We've proven that the exterior angle in this triangle, so this one, is equal to the two opposite angles here. Okay, so just to make it a bit more clear, right, this x here, this x is equal to the opposite angles, okay, and that is equal to x, the red x, which was our exterior angle. Okay, they've got the same value. Okay, hopefully that was useful, and thank you.